Hello guys, Alias theory builder lesson today. In this one we will talk about the construction options. I mentioned construction options multiple times in my modeling lessons, but never described the specific parameters, so I guess it is the time. So to open up the construction options, you go to the preferences, construction options, and you will open up this window. Now I will describe it from top to bottom. So first we have the construction presets. So basically this is the list of predetermined settings for the downstream CAD software, like, CATIA V5, there's a SolidWorks, there is Inventor, and there is always a user-defined. So you can pick any, duplicate, and then you will give an option to change it to your own likings, or in most cases to what your engineering department wants. So this is that. Now let's go to the units. Now, as you can see, there is two types of units. There is a linear units and the angular units. Now, it's kind of self-explanatory, but there is a nuance. So as you can see, there is a free options for linear and free options for angular. There is a main units, and there is a subunits and pause units. And on top of it, we have a scale factor. Now, these options, the subunits and pause units, are additional units for a measurement. Now, your main units is your main units, and everything in Alias relies on your main units, including all the tolerances. So if I will change the main units, let's say to yards for some reason, well, it will completely convert everything to the yards, except of the angular, they are still in the degrees, and I can change the to radians if I want, as you can see. So this is kind of like your main units, and when you operate with the translate, transition, rotate, scale something in a viewport, it will be relying on the main units. Now, what if you really want to use the subunits? And sometimes it becomes to be really helpful. For example, you have a blueprint and there is a small arcs, and these arcs, as they are really tiny, they measure it in minutes or even in seconds. Now, I had experience of working with minutes, never had with seconds, but I guess it's possible too. So how you activate the subunits? Well, let's talk about that. So let me just create the curve, and imagine that I will be using in the angular example. Imagine I want to rotate that on the 45 degrees, but not in the degrees, but in minutes. Now, if you, like me, will try to use the Gizmo and just kind of set that up, you can't, because Gizmos works only with the main unit. So I can set that to 45 and rotate it on 45, like simple as that. But if you really want to use the subunits or pause units, you need to use the transform tool. So we go to your transform tab in the main palette and pick the rotation tool. And now it basically gives me the full control over my rotation. So as you can see, I need to enter free values for all the axes, X, Y, and Z. So if I really want to rotate that using the rotation tool, I need to hit tab and type X for 0, X for Y, so I need to specify, and I think 45 for Z, yes, and we have a 45 degrees. But if I really want to use the subunits, the syntaxes will be different. So I'll click on rotate, hit tab. The first is the same, 0, 0, 0, so X, Y, and Z, all of them 0. Once again, we're not working with the degrees, we're working with minutes. After that, I'll type colon, and then I will enter the subunits, the minutes. Now, to understand 1 degree is 60 angular minutes, and 1 angular minute is 60 angular seconds. So you can open up the calculator and calculate it, but I actually did it for you. So to calculate it, to rotate it in 45 degrees in minutes, you need to use 2,700 minutes for that. So let's hit enter, and as you can see, it rotates in 45 degrees. Now, let me turn that back. And now, as the last example for the units, let's use the subunits and the pause units at the same time. So I will rotate 45 degrees on minutes, and then on 45 degrees on seconds. So let's do that. Click on rotate, hit tab, type 0, 0, 0 for my degrees, colon, and now 2700 for our minutes, and then another 45 degrees for seconds. It will be 145800, hit enter. And here we go. So we rotated 45 in minutes and 45 in seconds. And that's basically how it works. Now the linear works literally the same way. The last thing here is the scale factor. It's very simple. The scale factor is basically your multiplier. So it goes from, well, you can go lower with 1, for example, 0.1, which means that it will be multiplying on 0.1. So if it will type or move on 1 millimeter, instead it will move on 1/10 of a millimeter, right? Or you can multiply it on 2, and every 1 millimeter will be 2 millimeters, and 2 millimeters will be 4 millimeters, and so on and so forth. Same for the scale factor on the angular units. I never used the scale factor, but I believe that in some situations it may be helpful. All right, these are out of the way. Let's go for the tolerances. So the first one is fitting. And this is the most interesting one, and it actually have a really huge impact on everything else. Now, before we talk about this, I would like to mention that in most cases, the engineering department or your client and client's engineering department, if you're working as a contractor or freelancer, they will not give you any of those except of the continuity. So the continuity are the main ones, and everything else is designed to help you build to these continuities. So you rarely see the fitting values in the technical documentation. Well, sometimes you can, but that's a rarity. I would say the rational flag sometimes specified, but we will talk about that a little bit later. So, okay, curve fit distance. So we go to my example with the curve fits and just start examining it. Now, another note before I'll talk about the curve fit distance is that these parameters, it doesn't really mean that Alias will build to them. Alias will always try to build to perfection. So basically you have your continuity gap to 0.001, but in reality, Alias will try to build to perfect position, right? That should be like a 0 deviation. When we go to curve fit distance, Alias will always try to build to, well, 0 deviation. But it's not always can. And if it's can't, then it tries to fit it within your basically your tolerance. And if it exceeds this tolerance, even if you just kind of throw millions of spans in it, it will just show you an error and you will see this error. So if it's set to this value, doesn't mean it builds to this value. It always tries to build to perfection. And that's where this example comes into the play. So the curve fit distance basically tells Alias how accurate it should build the surface from the curve, or how accurately it should reconstruct the curve from the trimmed edge or another curve, or how accurately it will place your fillets to the surfaces. So basically, one way or another, anything relying to the quality of the surface built from the curves. Now, for example, I will create a square tool here, and let me just kind of untackle the explicit control. So let me just kind of undo it and just create, increase the curve fit distance to 1 millimeter. So it's very loose now. And I will create a square. Now, as you can see, Alias has little to no problems to create the surface around these curves, because these curves were very clean and accurate. 6 degrees, 6 degrees, 6 degrees, 6 degrees, they all positional. So for the square tool, it's not a big problem to create the surface. And it actually created it to the perfect position. Now we have a curve fit distance to 1 millimeter. So basically it kind of gives the ability to, so if the difference between the position of the curve and position of the surface will be within the 1 millimeter, it still will be positional, but this one is actually positional. So if I will go and check the distance between curve and surface, so this is my curve and this is my surface, there is a 0 deviation, even though the tolerance is very loose. Once again, Alias tries to build to the perfection all the time, and it's not a big brainer to do it here. In comparison, when we're going to the trimmed edges, so much more complex edges, that's where this stuff comes into the play. Now, let me show you first on the different example. Now, this is the surface which I trimmed by the curve. And when you have a trimmed edge. And these trimmed edges, especially if the surface is wobbling around and on the different axes, it's become to be pretty complex. So to really follow it closely by some other surface or create the surface using this side, it kind of needs quite a lot of controls, let's put it this way, for the surfaces. To illustrate that, let me actually do it loose first. So I will go to my profile tool and just create the profile along this trimmed complex line. So I select this, and click build. Now, as you can see, Alias has little to no problems to building this, and actually it's very, very clean. It's just only 6 degrees. You see, only 6 degrees. It's very accurate. All nice, right? Well, the surface itself is clean, but as we have a really big tolerance for the curve fit, it's actually not positional. You see? Now we have a deviation. It's a small one, but it is here. So to mitigate that if you really wanted to create the surface which will be actually touching this trimmed edge, and once again, this is a trimmed edge, it's not that clean as the actual clean curve, you need to make the tolerance much tighter. So I'll go back and type my original one, which is really tight, and then repeat the process. So select these one, and build. Look how much more complex this thing became. Now, first of all, there is a lot of spans, the 9 spans, and the surface is not that clean anymore, but the connection is positional. So it really achieved this position by bringing more spans to this profile. So the looser this value, the simpler the surface will be, but the less amount of chances that it will connect, especially when we're talking about the trimmed edges. Now, this is only one of the examples. Now let me create a square using this dirty edge. So I will use the square tool. I'm not using explicit control and basically relying on Alias. And once again, let me just increase the tolerance, basically lose the tolerance, sorry, and then just create the surface. Now, as you can see, as you may predict, the surface is really clean. The tolerance is high, so the surface is really clean, but it's not positional again. Once again, we have a small deviation in the for the position. If I will, on the other hand, tighten the tolerance back and then create the square again, look how much more complex it becomes. Once again, I'm not asking Alias to create the specific surface. I will do it a little bit later. So I'm not using explicit control and leave Alias to do the work. And it did, but it kind of brings, how many spans it brings me? It brings me 30 spans. Well, that's a lot. So obviously we can do it better and achieve position, but yeah, this is the automatic process, and just based on this curve fit distance, Alias was able to create me this. All right. Now let's talk about the next parameter, which is a curve fit. Oh no, one more thing I want to show you about the curve fit distance is the duplication. So because it relies on duplication too. Now let me go and just create the, once again, lose the tolerance, and I will duplicate the curve using duplicate tool. Now if I look here, there is a 6 degree single span. You already may predict it's not positional. Now I will lose the tolerance, tighten the tolerance again, and then use it again. Look, it's now 6 degrees, 4 spans. It's much more complex. It's not necessarily positional too. It may have some deviation. Actually, I don't know. Let me just check it. It may have, still may have, or maybe it will be perfect. Who knows? So curve to surface. Let's check. But I believe there is a small deviation still exists. Yeah, there is a still small deviation, but it's a 0.0003. It's very tiny. But the surface or the curve is much more complex. So they are definitely not identical. And once again, that's because of this parameter. Now, this parameter and the next parameter, all the fitting basically. All right. So now let's talk about the curve fit checkpoints. Now, the curve fit checkpoints is the how do you actually kind of explain this? It's it's technically a sampling rate. Now, how many samples Alias will take to, calculate the accuracy. It's kind of heavily used for the surface continuity tool. Now, actually, let me just kind of show it to you as an example. Now, I will create another square tool. I'll click on explicit controls, and let me just kind of see. I would like to be positional, so let me just kind of 5 degrees. How many spans I need? 1, 2, 3, 4, 5, 6, 7. Oh, okay, it's too much. Let's go 5. Let me increase the degree. All right, yeah. So I managed to achieve the position with less amount of spans manually, which is good. And now if you look here, we have all of these points. Now these points are the curve fit checkpoints, and they placed here by the surface continuity tool. Now let me just check this again. So this is positional. That's good. Now let me just delete the history and realign it to the curvature. Let me do that. Bam. All right, now it's curvature. Now let me delete the history again and check it using surface continuity tool. Okay, curvature. Now if I open this up, you will see that there is a few options, and one of the most important one for us is the per span method. So it's checking the curvature at these small points, and these small points are spread along this edge using the per span method, which actually using this value curve fit checkpoints and basically spread this amount of points across the span of the surface. So when I activate the surface continuity tool, you will see that I actually have the additional options for that in the information window. So check spacing by per span and the value checkpoints 10. This is the same value as you can see here. But when you activate the surface continuity tool, now you can operate with that. So the more checkpoints you have, the more accurate the readings will be. For example, let me increase it to, let's say 100. And check it again, and immediately the LS put me an error. Now this is the curvature deviation 1. Now let me just do maybe 30. All right. So you see, the more checkpoints you have, the more accurate reading you will get. Now, as original one was 10, and for the 10 it's perfectly continuous. For 20 checkpoints or 30 checkpoints, it's not. And by the way, a small hint. If you will, let me just deselect and use the surface continuity again. If I will use surface continuity, click on the middle mouse and drag to the right, it will increase the amount of checkpoints right here. Look at the top right. So click middle mouse to the left, to the right, it will increase or decrease the value on the fly. And this one is the standard one, which it basically uses by default. Now you don't really need to be crazy and go like to 100 all the time, because in most cases this is excessive, and even in most cases the 10 is more than enough. And if you have this 10, its curvature, you see that surface continuity tells you that everything is all right, and you use your diagnostic shadings, and if you see some discrepancies, then you increase the amount of checkpoints. But this is a rare occasion. In most cases it's supposed to be okay. But if it's not, well, you know where you can check this. This is the parameter which basically used to calculate this, basically brings the sample rate to the edge of the connection, to the connection where you can check your continuity. Well, this is the checkpoints. Now, the next one is the max surface span. So this is the maximum amount of spans tool can use to, well, create the surface. Now, the most prominent usage of it is the fillet tool. Now, technically, it's supposed to work for the square tool, for the freeform blend, for rail, for multiple blend surfaces, and maybe for something else. So almost for everything. But in practice, the most reliable solution, or basically the example to show you, is the fillet tool, because Sometimes square tool just doesn't care. It kind of should, but it's not always does. But the fillet tool does it almost all the time. So it's somewhat a buggy feature, and not for this version, but for a few years already. But I believe it's just better to show you in the fillet tool. So, and on top of that, talk about the curve fit distance as well. So I'm gonna have this surface. I will let it. I will just delete this and just recreate that, but this time to position. Right. And now what I'm gonna do is I would like to create the fillet between the two. Now I'll use the fillet tool, and I will decrease. No, actually leave it like this 10. So let me just click on this and build the fillet. Now I'm using existing theoretical, so we didn't really bend or do something. And as you can see, it creates free surfaces for me. Now that's because I am in the Bezier. If I'll uncheck the Bezier, it will create me this amount of spans. So there is like what the maximum amount is 10, and it creates me 5. Now if I will undo this and use the amount of spans, let's say maximum amount will be 2, and try it again, it will show me the error, or basically the warning, that it reached the max surface spans, which I set in my construction options. And it says that it may not be continuous. And in fact, yes, it's not. It's not even positional. So technically the same works for the Bezier surfaces, but the Bezier surfaces basically creates the separate surfaces, but you can use it as the amount of the surfaces, the quantity of the surfaces. So let me say that the maximum is 10, and it easily built me the transitional surface, the fillet with free surfaces. So we are within the max range. All right. And by the way, these curve fit distance as well into the play. So well, in this situation, this side is quite simple. So I believe even if I'll increase it to 1, it will not really change much. But let me just try. I don't know. Most likely it's still, no, it's not actually. With the curve fit distance of 1, it wasn't able to achieve the position. All right, that's interesting. Let's just increase it back to tighten the tolerance and then just create a surface like this. Okay, so as you can see, all of this free works in conjunction, and they have a really big impact on the Alias tools. So if you before relied only on these ones, well, the fitting, that's why it's on the first place. It's kind of like the fitting first and then continuity second, because this one is one of the crucial parameters actually to achieve the proper desired continuities. Right, so this is about the fitting. Let's go next and talk about the continuity now. So continuity. I think there is nothing here, right? Yeah, I need to build it myself. So continuity. Well, the first one is the continuity for position. It is G0. The normal angle G1 is a tangency, and continuity curvature G2 is curvature. So position is extremely simple. It's just the position. So we have a position deviation for 20 millimeters. Our gap is 0.001. Now, obviously, that's not positional. That, I guess, it's self-explanatory. What's about the tangency? Now, really simple too. Now let me just create a couple examples here, like this. So curve 1, curve 2, are they tangential? No, because for that stuff to be tangential, it should be on the same vector and have the same direction, but it's not. Now let me check this. How big is the deviation? So oops, come on, right? All right, so yeah, we are away from miles, so this is 45.8 degrees deviation for the tangency, and the tangency deviation measures in angles. Now let me align it now as a tangency back, and now if I will check that, I will check that again, and as you can see, there is no deviation, and in terms of the degrees, I'm not just within the 0.05 deviation, I'm literally spot on, as you can see, 0.0. So it's perfectly tangent. Right, now what's about the curvature? Well, Curvature is a tricky thing. I actually made a separate video called the deviation 1 error. I probably supposed to be somewhere on the screen right now. If it's not, I will link this video into the description to this one, where I explain in all the details how Alias calculates curvature. Because it's not that simple. It's not like G1 and angle and that's it. It just have much more. But just in case you don't really want to watch that video, but just have a brief understanding, basically what will happen is that at the point of connection, Alias creates a circle and fit it perpendicularly, and then it basically scales, it fits the circle and scales it until it describes the curvature of the curve, right? Now, how big the curve curved. Now let me just kind of do it like this. So there is like some kind of a circle here. Just quickly describe that and just kind of scale it down, move it out, and just kind of fit that. And it just tries to fit the circle, kind of set the radius, which will describe the curvature of this curve or surface at this point. And that it's not perpendicular actually. So the perpendicular is supposed to be somewhere, oops. Come on. All right, there. So it's just pretty much what Alias does. So you have the point of connection, there is a curvature, you need to check it. It creates a perpendicular line, place a circle, calculates the radius of the circle to this side, and then another one to this side. And if they are spot on, these radiuses are equal. If they're not, so there is a slight deviation. Now it takes these two radiuses and then compares the two using the specific formula. Once again, if you want to know the details and learn about the deviation 1 and how it operates and what is reciprocal for these radiuses, just go check that video. Once again, it's somewhere here, I believe, or in the description. But basically, eventually, it will get some value. And this value is not a degree. It's actually a linear measurement, so the linear value. And then it uses this as the and you see it in your tolerance. So this 0.05 is a linear value, the difference between the two circles, which describes the curves, and that's how it basically calculates the curvature. Okay, so now they are, as I mentioned before, these three are something you will get from the engineering department, and the fitting is something you rarely get. Now we go to the next one, which is topology. Let's go to the topology. Now topology is it's actually quite interesting. Now the topology, just how to describe it, is basically, you know, when you have the basically two different pieces of an object. Now you definitely know as a modeler, are these parts the part of the same part of the model or the same model, or they're two different pieces? But Alias doesn't know that. So basically this topology distance is kind of like tells Alias what surface is adjacent, so which surface is adjacent to which. Now, is these surfaces adjacent or are they not, and they just the parts of the different model? Now, this parameter used by both surface continuity tool and the check model tool, I believe for the transform rig as well, but I will not bet on that. I'm not using transform rig. But these two, the check model and the surface continuity, they're actually relying on this topology distance. Now, let me show you how it works. Let me show you on an example of the topology. So, sorry, on the check model. So let me open up the check model tool. Now we use check model tool to evaluate our models for different types of errors. So as you can see, my topology distance is set to 0.02. It's pretty tight. My gap here is pretty big. Now I don't know which one, how big it is. Let me just kind of measure that. So my gap is 0.3 and the topology distance is 0.02, very small. So that means that if I will go, let me just kind of use my topology, not use anything else, and perform the check, it will not return me any errors, like any errors whatsoever, because the adjacent check happens on the much smaller distance than this gap. So Alias knows that this surface is not adjacent to this. The distance is too big, and it didn't really tell me that there is any errors. But if I will go in and manually increase the topology distance, I can do it right here actually. So I just kind of go and just type the proper value instead of changing it here. But I can change it here and perform the check again. Now it immediately returns me an error, because right now within the 1 millimeter, and it just treat everything here within the 1 millimeter, is that they are adjacent to part of the single model. And then Alias immediately see the gap here and like, well, they're supposed to be the single part or the part of the adjacent structure, and it's not. So there is a gap. Now deal with it. So yeah, this is how it works. Pretty much simple as that. Let me just go back to the original 0.02, and as you can see, it doesn't really return me any errors anymore. So one note is that if the edge is already filled with something, so it's already positional to something else, Alias is smart enough to understand that it's a closed part, and this one is separate, even if it is within the topology distance. Now, once again, let me go override it to 1 millimeter, so it will take it into consideration and check. And as you can see, no errors. Let me hide this one and then check again, and immediately we have an error. Right, so this is about the topology distance. Now, let's go next. Now we have, we have trim curve fit and max gap between curves. Well, this one is this one. So this one is really confusing, but not because it's difficult to understand the concept, it's because of the naming convention. Now, they call that trim curve fit. In practice, what it does, it's just like, it sounds like you trim something and the quality of the trimmed edge. But no, it's actually about the quality of the projection. So I have my curve, and I projected it on the surface, and then another curve, the same one, and projected it on the same surface, but with the different tolerances. This one is within the tolerance of 0.01, and this one I believe in 0.1, don't remember. But if I look from the side and zoom in to the looser one, you will see that there is a gap. Now let me just kind of do it like this. Now I believe it's kind of visible here that it's kind of visible, right? It's not clean. And that's because this one was set, I believe, to 0.1 or something like this. Now this one, in the other hand, let me just go back up. This one was projected within these value 0.001, much tighter. And if you zoom in, you will see that it's actually much cleaner. Now, it's not spot on. Once again, there is still deviation. So if I will zoom in and I will zoom in and I will zoom in, I'll probably see the difference. Yeah, you see there's really tiny deviation within them, but really small. In comparison, once again, let me just zoom in. Now, yeah, it's already visible. So how big it is, right? It's huge, I would say. So that's what it does. This is the curve trim fit. So the tighter it is, the more accurate the projection will be, but at the same time, the more complex it will be. So let me just go and duplicate this. And there's like 23 spans. Let me duplicate this. And this one even 11 spans. No, so it's actually become to be even cleaner, actually, a little bit. Let me just delete this. Okay. Right, so what's about the max gap between curves? Where is this example for that? Oh yeah, here it is. So max gap between curves. Well, this is technically what it is. If I will zoom into the circle, closer and closer and closer, there will be a small gap, but intentional. And then I will project it using the trim curve fit of 0.001 and project it on the surface. Now, if I will zoom in, you will see that there is a small gap here. Now, technically, when with the tight gap between curves of 0.001, it calculates this distance and says, there is a gap, I don't want to trim that, there is an error. But if I will increase this and try to trim it again, it says, yeah, perfect, I'm willing to trim, And if you do, it will perform the trim. I'll actually show you. Now, in fact, this is not beneficial. So if you say, well, that's so awesome, there is nothing awesome in that, because what Alias will do in the loser tolerance, which I suppose it actually never supposed to do it. I don't know why Alias just leaves as an option to do so. Because when we have this basically gap, what Alias will do, it will automatically create the curve and surface, just a straight line, and connects that without bothering of any continuity. It will trim it, yes, but next time when you will try to build from this trimmed edge or build to this trimmed edge to kind of transitional surface or fillet or whatever, at this point you will have a hard time, you will have a lot of spans, it will probably be, there will be no curvature, and that's only because of this small gap which Alias closed by itself, because you have a pretty loose tolerance in the max gap between curves. So a good rule of thumb is keep it tight, so you don't really encounter these problems. All right, this is about the curve and surface trim. What's about the rational flags? Now, the rational flags are, let me just kind of turn on the rational flags. Now, I will do a separate video. I actually kind of mentioned it a few times as well, but I will do a separate dedicated video about the circles where I will be explaining the rational flags in detail, like with all the nuances. But once again, it's in the construction option, so I still need to mention that. So the rational flags are the different type, it's basically a switch for the different type of circle calculation, how Alias performs math around the circles, because there's different types of circles Alias can do, and there is a different math behind them. Well, rational flag designed to create a perfect circle. So when I say perfect, I really mean it, like the mathematically accurate circles, and actually like with zero deviation, let's put it this way. Now, the nuance with this is that there is two checkboxes, one for the primitives and one for the curves and surfaces. Let me actually show you the example. So let's go and just create the curve here, a circle, sorry. And actually, let me just do it this way. Sorry, guys. So I will do one non-periodic, 4 segments, 3 degrees, and then the same one, but with the rational flags. All right. So as you can see, they're both identical. These without rational flags and these with the rational flags. If I'll use the radius to check that out, it's wobbling around. It's not even close to be accurate. And these one, surprisingly, perfectly accurate. Well, how can that be? Well, that's because this one is under the rational flags that have a different math. It's the different algorithm to calculate it. And now visually, as they look completely identical, right? But actually there is a difference. Now visually, the circles with rational flags have different weights for the CVs. Now in the non-rational flags, if I'll select the CV and go to the information window, weight is 1, and this one is 1, and this one is 1, everything is 1. Now these CV weights, basically the parameter which describes how much this or that CV contributes to the form of the curve or surface, how much it affects it. And by default, without the rational flags, all of them behave the same way and have the same effect, which is beneficial in a lot of ways. But when you switch to the different math in the rational flags, then these CV weights are distributed differently. Now, Alias does it automatically, so we're not really affecting this, but some of the CVs are still weight 1 and some of them are 0.8, you see, so it kind of like changes it. It changes the amount of a contribution, and by that making circle with a perfect shape. Now, you can do these ones kind of perfect in terms of the radius reading, but if you're talking about the pure math, these ones is the proper ones. Now, as you can see, there is two checkboxes, one for primitives, one for curves and surfaces. It says and surfaces because you can create revolves or the profiles from these rational flags, and they will have this rationality with them as well. Now, the primitives is very simple, just primitives. Primitives are spheres and cylinders. So let me just kind of quickly illustrate. So this is the cylinder. And, oh, sorry, let me just go an example to the sphere. So this is the sphere without the rational flags, and this is the sphere with the rational flags. As you can see, they're different. Now, this one will be perfect, this one will be not. Okay, so, and once again, all of this rational flag stuff is affecting only circular shapes. So circles, it's designed to create a perfect circles and perfect circular surfaces, revolves and sweeps from them. It doesn't affect anything else. And it actually really tied to the different types of circles. I just really briefly touched it here. But the next video will be specifically about the circles and about the rational flags, so stay tuned. Okay, so that was about the rational flags. What's about the fonts? Well, that's really simple, right? So let me just kind of create this. This is the font. This is the size of the font. You can increase it or decrease it. And this is the display mode, fixed side scale. I believe in this version of 2025, it looks like it's bugged a little bit. And we just, no, it looks it just does something, right? Yeah, okay. But I prefer using fixed size and just a smaller value. But this is just the font, so this is pretty simple. All right, so now let's, as we already covered everything here, let's talk about the standards within the industry. So what kind of a preferences, what kind of a settings you need to use to achieve the desired result. Now, for the consumer electronics, which I'm in, we are working with a pretty tight tolerances, and you actually already see them here because they are from my, well, everyday job, if you will. So if you're working with the really kind of tiny pieces, like, you know, different parts of the phones, you know, then different type of consumer electronics, from keys for the car to remote controls to headphones, phones, mouse and keyboard, you know, stuff like that. You work with the pretty tight tolerances, especially for the gaps, and pretty picky for the curvature, especially if you're working with the expensive materials and on expensive products. Now, the fitting parameters are never specified. Once again, I already mentioned that before, but these ones, as you can see, are fit perfectly to the consumer electronics. It kind of, these ones, all of them are designed to achieve these desired continuity tolerances. Now, if you're working, but this is the consumer electronics. If you're talking about the, let's say, car industry, then the biggest difference is the positional gap. So, and once again, it really depends on what kind of a manufacturer you're working for, what kind of a design bureau you're working for, externally, internally. But in general, if you're working with the cars, and specifically for exteriors, then the positional gap will be 10 times loose. So it will be 0.01 millimeter instead of a 0.001. So what I mean is that it will be like this for exteriors, and probably 0.1 for tangency and 0.1 or sometimes, yeah, in most cases 0.1 for the curvature as well. Now, but this is for the exteriors. When we're talking about the interiors, then it really depends on the object. If this is a big stuff like a seat or the you know, kind of paneling, the door panels, you know, stuff like that, that's pretty much true to the same tolerances as the exterior. But when we're talking about the dashboard, or like the console where there is some bezels, a screen with a lot of buttons, small fittings and gaps, then the tolerances will be pretty much the same as the electronics. So There is two kind of like extremes now. So one of them is really, really big objects, and one of them is really, really small objects. Now, I never worked in my career with the really big projects, like, I don't know, Iowa class battleship, right? Or battle cruiser, I don't know what it is, 100 meters long, 50 meters high, stuff like that. As I don't have experience working with that, I don't know what kind of tolerances they have. And in most cases, you probably will rarely do it in Alias. But I believe that it will be much looser than the car. So it will probably be like 1 millimeter or 0.1 millimeter for the position. And another extreme is really small stuff like Javelry. So if you're talking about the Javelry, the positional continuity can be even smaller. It can be like 0.0005, and the tangency can be 0.001, and the curvature can be 0.001, so 5 times tighter than the consumer electronics can. But once again, it really depends on the type of the Javelry. Is it like a real Javelry, or just like some fake shit, right? But once again, these two, the super big ones, the super small ones, are really extreme. Now, if you are working on the fictional stuff for, I don't know, gaming industry or for the renders, and no one really give you these tolerances, you basically need to set them yourself, then I suggest you to go instead not with the consumer electronics as I do, but instead go for the car tolerances for exteriors, because it doesn't really matter. It's kind of a good sweet spot between the big and the small shapes. So as in polygons, at the end of the day, it's all somewhat relative. You can build a Death Star, or like a car or a gun, prop for the gun. You just need to have a middle ground to accommodate all the sizes, and be sure that your fillet tool and your fittings will not be crazy or all over the place, right? So I suggest you to work with the car tolerances in terms of the position and the tangency. So it means 0.01 millimeter for position and 0.1 for the tangency, same for the curvature. And you should be golden. So after the tessellation, there should be no errors. All right, guys. So this is pretty much it about the construction options. Thank you very much, and I'll see you in the next one.